you have the whole Easter break to work on it, if you haven't already done it. And if you have any questions on the art coursework, you can email me or Zoom me 24/7. And I'm glad to let you know that I will be in Manchester throughout the Easter break. I will be in Manchester throughout the Easter break. So if you have any questions, just drop into my room. You know where to find me, okay? All right? Is that clear, guys? All right, now, on Monday of this week, I started talking about test of hypothesis, right? There are a few things you need to know about test of hypothesis. The first one is known as the null hypothesis, which is the hypothesis to be tested. For example, the average weight of men is equal to 70 kg. That's an example of a null hypothesis. The second one is the alternative hypothesis, denoted by H1, also known as the research hypothesis. An example of a alternative hypothesis is the average weight of men is less than 70 kg, right? Or it could also be greater than 70 kg, or it could also be not equal to 70 kg, right? So that's an example of an alternative hypothesis. Now, a test statistic is a function of the data. So capital T is a function of the data that is used to determine whether H0 or H1 is true, right? And the rejection rule, sometimes it takes one of these forms depending on what you're trying to test for, right? Where K is a constant, right? And a rejection region is a set of all data, belonging to the sample space S such that the rejection rule holds, right? That's known as the rejection region. And are you guys listening or what? That's the rejection region. And finally, the acceptance region is a set of all data belonging to the sample space such that the rejection region does not hold, right? All right, this set is known as the acceptance region, right? All right, guys. Right, now then I talked about, this is kind of a summary of what I did on Monday, if you were not here. This is kind of a box, right? It has two dimensions. On the row, the row indicates the decision that you make. Either you reject the null hypothesis or you accept the null hypothesis. So it's one of two possible decisions you can make. The column, it indicates the state of the nature of the problem. The state of the nature is something only the God knows it, right? We humans, you have no idea whether it's going to rain tomorrow or whether it's going to be sunny tomorrow with 100% accuracy, right? Only one person in the world knows that, right? So the state of the nature can be either one of these two, right? Either H0 is false or H0 is true, one of these two outcomes, right? So if you look at this box here, there are four possible outcomes, right? So H0 is true and reject H0. H0 is true and accept H0. H0 is false and reject H0. H0 is false and accept H0, right? And of these four outcomes, two of them are correct and two of them are not correct. And this one is known as the type 1 error, and this one is known as the type 2 error, right? So type 1 error is the probability of rejecting H0 when H0 is true, and type 2 error is the probability of accepting H0 when H0 is false. And these two errors are bound to occur in any kind of test of hypothesis, right? It's impossible to eliminate, as I said to you on Monday, it's impossible to eliminate the probabilities of type 1 and type 2 errors. But what you can try to do is you can try to minimize the chance of type 1 and type 2 errors occurring. Okay? All right. So that's stuff we did on Monday. And then some notation I gave you. This is the notation. Alpha. Alpha denotes the probability of type 1 error. Beta denotes the probability of type 2 error. And alpha also used to denote what is known as the significance level of the test, right? So this is some notation. Right. Then I talked about one sample test. These are one sample test for the population mean when the variance is known. So you have a random sample from a normal distribution, and we are assuming that sigma squared, the population variance, is known. In this case, there are three possible tests. This is known as a two-sided test because your alternative has mu not equal to mu 0. It can be either left or right. And these two are known as one-sided tests because here the alternative is greater, here the alternative is less, right? So for each of these tests, these are the rejection rules. So for example, this one, you will reject the null hypothesis if this is true. Yeah? For this one, you will reject H0 if this is true, and so on, right? So that's stuff we did. And this is test for the population mean when the variance is unknown, right? So in this case, the rejection rules are similar, except instead of using Z, whatever, you use the t-table, right? By the way, if you had been to my tutorials, I would have explained to you how to read the t-table and how to read the Z-table. But I know some of you do go to the other tutorials. So if you don't know how to read a table, please come and see me in my room, ATB 2.223, okay? You follow what I'm saying? If you don't know how to read a Z-table, if you don't know how to read a t-table, or if you don't know how to read a chi-square table, please come to my room, right? Okay? So these are the rules. And then number 3, here we are testing for the population standard deviation, right? So these are the 3 sets of hypotheses. So sigma, remember, is the population standard deviation versus not equal to versus greater than versus less than. And these are the rules for rejecting the null hypothesis in each case, right? And here you need to use the percentiles of the chi-square distribution, which you read from the tables I just mentioned a few minutes ago, right? Okay? All right. Now, number 4, which I'm going to do now. So this is number 4. Number 4 is about testing for population proportion. So suppose suppose you have a random sample from a Bernoulli distribution with parameter p. Remember, Bernoulli is a distribution that takes either 1 or 0, right? So for example, like smoking or not smoking, or having a car or not having a car, or having a TV or not having a TV. It's things like that, right? Either 1 or 0 is the possible outcome, right? So here, you're trying to test, once again, 3 possible hypotheses. All right, there are 3 sets of hypotheses. So like, for example, P could represent the proportion of smokers. So you could test, for example, whether the proportion of smokers is equal to, say, 20%, right, versus it's not equal to the 20%, right? Okay, so the rules for rejecting are as follows. So you reject, in the first case, you reject H0 if right? So this is the rule for rejecting the null hypothesis for the first hypothesis, right? For the second one, right, this is the rule for rejecting the null hypothesis. And for the final one, right? So these are the 3 rules for the 3 sets of hypotheses. Okay? You guys okay? So these are so I talked about 4 sets of 4 one-sample tests. The first one is for the population mean when the population variance is known. The second one is for the population mean when the population variance is unknown. The third one is for the population standard deviation. And the fourth one, which is the one I did right now, is for the population standard deviation, right? Now, I mean, as I said to you before, I mean, I try to do a lot of examples. So I promise you guys to do 10 examples on everything. So let's see if I can do them. So number 1, I mean, you learn things by example. So suppose right? Okay. Right. The example here is the following. So you have a random sample from a normal distribution, and we are testing this versus this with H0 rejected if this is the case. And we want to find beta. Remember, what is beta? Beta is the thing I just mentioned to you. It's the probability of type probability of type 2 error, right? It's the probability of, do you remember what a type 2 error is? Huh? You accept yes, all right. Now, this is the rule for rejecting the null hypothesis. So you will accept the null hypothesis if the probability of root of n times x bar minus mu 0 divided by sigma is less than or equal to yeah. You guess with me so far or not? Right. Now, we are conditioning on the fact that the population mean mu is greater than mu 0, right? Now, you may recall that, I don't know whether you remember this or not. You may recall that if, I'll write it down here, if you have a random sample from a normal distribution, then, I mean, I mentioned this many times in the class. What distribution does this have? It will have a normal distribution with parameters. Yes? Yeah? And this implies that root of n times sigma multiplied by x bar minus mu will have a normal distribution with parameters 0 and 1. Yeah? Do you remember this? I'll put this in the box, guys, so that you may recall this. Yes? Yeah, so I'm going to use this fact, right, to simplify this, okay? So let me put this over here. And then go back to here. So this becomes yes? Yeah, you see what I've done? I have subtracted a mu and added a mu, so I haven't changed anything. And the reason I'm doing this is because to use this fact here. So I'm going to put brackets around here and the brackets around here, right? And then You see what I've done? I've taken the second term I've taken the second term over here to the right-hand side, so it becomes this, right? Now, using this result here, guys, we know that this guy here, because we are conditioning on the fact that mu is greater than mu 0 is the true population mean, this must have a standard normal distribution, right? So what you have here is the probability that okay. I'll remove the conditioning here because okay, when I made the argument that conditional on mu, this has a standard normal, I have used the conditioning, and therefore it is no longer needed, right? I used the conditioning. So what you have here is phi. Remember, phi is the CDF of the standard normal at all right. To complete the question, so what we have shown is that we have shown that the probability of type 2 error is equal to this, right? So we have shown, right, this is the probability of type 2 error, right? So that's example. Do you have any questions on this example, guys, or not? Yes, ma'am. Yeah, the reason I remove the conditioning is because this expression here has a standard normal distribution given the fact that the population mean is mu, right? If the population mean is mu, then this guy here has a standard normal distribution. So I've used the conditioning that the population mean is mu, right? Because this is a condition that the population mean is mu, right? So when I argue that this has a standard normal, I've used the conditioning. Therefore, it's no longer needed, right? So, okay. I know it's kind of slick argument, but that's how you do it, things. Yeah. I mean, when I do more examples, hopefully it will become clearer to you guys, right? Okay. All right. So that's example 1. Let's look at example 2. Hopefully, I will have. I don't know how many examples I would do, but. This is all right. Example 2 is the same as example 1. I mean, if you want to know, this is example 1. Then hopefully you can see this here. This is example 1, guys, right? It's the same as example 1, except the rejection rule is different, right? And we want to find, once again, the value for beta, right? So beta is the probability of type 2 error which is the probability of accepting H0 when H1 is true. So this is the probability that this is the rule for rejecting, right? The probability of accepting would be x1 minus mu 0 divided by sigma less than or equal to z. Okay. Right, now, okay, here I'm going to use this because we know x1 is just the first data point, and we know that each of the data points, can you guys listen please? We know that each of the data points has a normal distribution with parameters mu and sigma squared, right? All right, so I'm going to use the same trick as an example 1. Okay. Now, I put brackets around like this. I'm going to pull the second term to the right-hand side, so it will become like this. Right now, let me test your memory. What distribution will this have, and why? Remember, x1 has a standard. It has a normal distribution with parameters mu and sigma squared. So x1 minus mu divided by sigma will have a standard normal. Yeah. So this will become right. Again, once again, I'll drop the conditioning here because of the condition on mu, being the population mean, this has a standard normal distribution. So I use the conditioning. Yeah. All right. So this becomes this. So this is all right. So hence, what we have shown is that we have shown that beta is equal to this, right? So that's example 2, guys. I hope you follow this. Any questions on this, guys? Hello, guys. Are you okay with this? Yeah? Yes? No? Oh. All right. So that's example 2. Now let's look at example 3. Maybe I will. Right, in this case, this is the same as example 1, but we will reject the null hypothesis if the following holds, right? this is I, so this letter I. Right? Okay, and the question is the same as before, find beta. So you follow what I've written. It says we reject null hypothesis if I is a random number between 0 and 99. If I falls in the interval from 0 to 4, yeah, so it means either 0, 1, 2, 3, or 4, right? So yeah, and this you can write as by the complement rule, you can write this as reject H0 when H1 is true. Yeah, and this is, all right, the rule for rejecting the null hypothesis is that the integer I is between 0 and 4. And H1 is true if mu is greater than mu 0. Okay, this is your probability 1 comes in. Now, can somebody tell me what this probability is? The probability that I is between 0 and 4. You guys okay? Come on, yeah. And you did probability 1, right, last semester? Yeah. So what's the probability of this happening? You forgot to know what? Now, how many possible values I can take? 0 to 99, there are how many? You have 100 values, right? All right, and between 0 and 4, how many values you have? 5. So it's 5 divided by 100. That's it. This is classical probability. I thought you did it last semester, right? Is it not? So the answer is 0. The answer is 0.95. Okay. Yes. You guys okay? Yes or no? Okay. So that's example 3. All right, now, I don't know whether I can do all 10 today, but I'll try to do as many as I can, as many as possible, right? So the next one, oh, by the way, if you haven't been to any of the example tutorials this week, could you please come to the ones this afternoon? There's a tutorial from 1 to 2 in G209 and 2 to 3 in G207, right? Please do come to those, all right? Okay. All right, this is example. Okay. right? Come on, guys, listen, please. You want to test the hypothesis that Can you read my writing, guys? So you have a bag containing 20 balls. Some of them are defectives and some are not. And so P is the proportion of defectives, Y is the number of defectives, right? And we want to test the hypothesis whether P equal to 0.2 versus P not equal to 0.2. And we will reject the null hypothesis if Y is greater than or equal to 7 or less than or equal to 1, right? Okay. Okay. And we want to find the probability of type 2 error. Let's see how we can do this. Right, this is the probability of type 2 error, which is now this is the rule for rejecting the null hypothesis, right? So what's the rule for accepting the null hypothesis? It will be if Y is between right, if Y is between 2 and 6. Remember, Y can only take integer values, right? Okay, so the complement of this event, right, is the event that Y is between 2 and 6 inclusive. Okay. Now if Y is between 2 and 6, the possible values you can take are either 2, 3, 4, 5, or 6. So you can write it like this. You can write it as 2 to 6 of the probability that Y equal to I, given that P is not equal to 0.2. Okay. Now this is where your probability 1 comes in. Yeah. Remember, Y is the number of defectives in a bag of 20 items. So what distribution will it have? Don't tell me you don't know. Didn't you do this in probability 1 last semester? You have a bag of 20 items, or 20 balls. Some of them are defective and some of them are not defective, right? Yeah, and Y is the number of items that are defective. So that will have Come on, guys. You got you've seen this before? What is this distribution known as? It's known as the binomial, right? Remember, the binomial is like a sequence of trials and some of them are successes and some of them are failures, right? And the binomial distribution describes the number of successes. So in this scenario, you could think of success as being defective and failures as being not defective, right? And y represents the number of defectives. So therefore, it must have the binomial distribution with parameters 20 and p. All right, so what we have shown that beta, the probability of type 2 error, is equal to okay, so let me put this in a box. Here we are. So this is example number 4. Are you okay? Are you okay with this, guys? Okay. Next one. Example 5. All right, so here we are testing for, we have a random sample from a normal distribution with parameters mu is the population mean and variance is 4. We are testing this versus this, and this is the rule for rejecting the null hypothesis, and we want to find beta, right? So this, all right, so this is the probability of accepting the null hypothesis, which is root of n times x bar divided by 2 less than or equal to z 1 minus alpha, given that mu equal to 4. Okay? Okay, guys. Now I'm going to use, if you go back to the slide I showed you earlier, it's this one here. I'm going to use this property here. Do you remember this one? Yeah? So to do that, I'm going to, because the true population mean is equal to 4, right? So we need to introduce this term here on the left-hand side. So I'm going to subtract a 4 and add a 4. So I haven't changed anything. Okay, you see why I'm doing this? Because I want to use this property, right? That this guy here has a standard number, right? Okay. So this becomes root of n times x bar minus 4 divided by 2. I'm going to take the last term to the right-hand side. So it becomes 2 root of n. Okay. Right, now using this property, what you have here has a standard normal, right? So this is the probability that okay, and we don't need the conditioning anymore because this has a standard normal condition on the fact that mu equal to 4, right? And therefore we use the conditioning, right? So this is phi at z okay. So we have shown that beta is equal to phi right. So this is example 5. Hopefully next time we meet, that'll be after the Easter break. I will try to do more examples, get it close to 10. But in the meantime, if you haven't been to any of the example classes, I would like to see you this afternoon, right, in G209 or G207, right? Okay. All right, guys. And also, if you have any questions on the R coursework, please feel free to contact me during the Easter break. Hey. Hello, how are you? What's your R coursework? Good man.
I have a question on the first one, the proportion one.
Yeah.
Like the first slide of today.
This one.
Yeah. Like why this one is alpha instead of 1 minus alpha?
Oh, yeah.
It should be.
It should be 1 minus alpha, yeah. Yeah, you're right.
Okay.
Yeah, sorry, you're right. It should be 1 minus alpha. Thank you. All right, thank you, man. Have a good day. Have a good break.
Yeah, you too.
Yeah. Yeah. Two to 6. It's because it's the complement of the. If y is greater than or equal to 7 or less than or equal to 1, is it 10 or 1?
I think you realized 10.
Is it 10? Oh, sure. It says 1 here.
Oh, so it's 1.
It's 1, yeah. It's 1. It's not 10. Yeah. Hello, sir. Hello, Michael.
About the arcos,
Yeah.
you know, I think it's part 5 where it says superimpose the graph you get in part 4
Yeah.
of the graph. Is it okay if I use the fit distribution part?
Yeah.
If you just use the plot k function.
Yes, you can. You can use it, yeah.
Okay.
Thank you, man. Hello, sir. How are you?
Here. I said use this. I don't understand how you use this. What does this condition imply? What is this?
The one I wrote down here, just a minute.
In the red box?
Yeah, in the red box, you have it? Yes, yes.
Yes, I understand it.
Yeah. Hello, sir. You have a question? This has a standard normal. Yes. Yeah, that's what doesn't matter because
Then what, that doesn't say anything. Because it doesn't matter. I don't get, what is the point of writing if you can't see the information from it?
no, what it says here is that the true population mean, mu, is a number greater than mu zero, right? It doesn't matter what mu zero is. It's just mu, right? The true population mean is mu. That's what it says. That's what the condition says. So condition on that, because of this, because of this has a standard normal. Okay, let me pack up because just wait outside. I will talk to you in a minute. I'll talk to you, man.